hydrostatic pressure. Hydrostatic pressure, the term itself, is just one of those things that makes you sound smart. But the concept itself also seems really intimidating. Good thing it's actually pretty straightforward. Most professionals already understand much of the concept intuitively in that they're attentive to drainage in every design and every detail. Even so, I think it does us some good to also know the science behind the concept. For water to become a problem for our enclosures, there needs to be some sort of driving force pushing it to the interior. For masonry buildings, that force is often capillarity, water wicking through a porous material, like you see when you dip a paper towel in a cup of water. But for framed buildings, the main force we're contending with is often hydrostatic pressure. There are other forces, but the main one we're typically contending with, and the one that happens to be least understood, is hydrostatic pressure. Hydrostatic pressure is the pressure that water exerts against a surface when it's held up against that surface. This is why we talk so much about drainage, i.e. not allowing water to be held up against whatever surface. But there's some value in going a bit deeper than that, so stick with me here, it'll be worth it. The equation we use to express hydrostatic pressure is this, where pressure is equal to the density of the fluid times the acceleration from gravity, the gravitational constant, times the height of the column. I'm pretty sure you won't ever have to actually use this equation. I never have. But it's really helpful to understand the variables at play, so we're going to go through it together. What I want you to notice are these two variables. Since the fluid we're talking about is water, and since we're only concerned with what goes on here on Earth, two of our independent variables don't change. And that makes hydrostatic pressure entirely a function of height. But what do we mean by height? We mean the amount of water that's been permitted to accumulate vertically. The classic example is a dam. This is a picture of the Hoover Dam. The reason the Hoover Dam has to be so strong isn't because of the volume of water in Lake Mead. It's because of the lake's depth. The dam has to be really, really, really thick at the bottom, but not so much at the top. It's 660 feet at its base, by the way, and 45 feet thick at the top. In any case, the pressure that water exerts on the Hoover Dam, 1 inch below the surface of the lake, is exactly the same as the pressure that water in your glass of water will exert on the glass 1 inch below its surface. This is why we describe hydrostatic pressure in inches of water. 1 inch of accumulated water against a dam, a cup, or a building's wall exerts exactly 1 inch of pressure. Now, for context, 1 inch of pressure is the equivalent of about 250 pascals, which is roughly the pressure exerted by a 45 mile per hour wind. The National Weather Service classifies that 45 mile per hour wind as a gale force wind. It's hard to walk in that kind of wind. Smaller tree branches will break. Now this, hydrostatic pressure, is why it's so important for us to not let water become what's called perched against our walls. It's why we need a space for drainage behind our claddings, and it's why we should always slope roofs, plaza decks, and balconies to drain. Always, always, always. Here are a few examples of bad designs related to exactly this concept. This is a typical residential 2x6 wood-framed wall with a mechanically attached water control membrane and a brick veneer cladding. There's a space for drainage behind the brick veneer and the water control membrane, but that space has been clogged with mortar droppings. Those mortar droppings will allow water to accumulate. Hydrostatic pressure will drive accumulated water to the interior through fasteners and laps in the water control membrane. If we had a clear space there for drainage, we'd still get water in that space and we'd still have laps in the water control membrane and penetrations through it. But we wouldn't have hydrostatic pressure to drive water along those pathways and into our building. Here's a commercial window detail, also with a brick veneer as the cladding. The rough opening has been extended using a metal angle, but sealing the bottom of that angle to the water control membrane at the sheathing will allow water from a leaking window or a failed sealant joint to accumulate, and hydrostatic pressure will drive it to the interior through the fastener penetration, holding that angle in place. Leaving the metal angle unsealed would prevent or greatly reduce accumulation and permit that water to drain into the cavity. The thing that lots of people get wrong about water management in buildings is that they make it primarily about pathways to the interior and the products we use to seal those pathways. And that is wrong, wrong, wrong. Relieving the driving forces that push water into our buildings is more important than sealing the pathways. This is because, one, it is simply not realistic for us to seal all of the pathways, cladding attachment fasteners being the most obvious things that are hard to seal. And two, no water control membrane, even if it's fluid, even if it's self-adhered, is sufficiently self-sealing to resist hydrostatic pressure at joints and penetrations, particularly at those that are unsealed or imperfectly detailed. We are always having to rank our priorities in design, and it's in this area that the science really helps us. We know that sealing potential pathways for water intrusion into our buildings is important, and we know that providing drainage is also important, but it's often difficult to do both of these things perfectly all the time, given all our other project constraints. And this is why it's so helpful to know that we can afford some imperfection in sealing our pathways, and indeed we should expect this kind of imperfection, as long as we also mitigate the forces that drive water along those pathways. That's the part that isn't always intuitive. We obsess so much about sealing everything up that we forget that the real juice is in avoiding the problem in the first place by providing drainage. For example, if I were waterproofing a typical basement wall and I was offered the chance to either A, the best, top-of-the-line, most expensive below-grade waterproofing membrane, or B, commodity drainage mat connected to a working perimeter drain, I'd choose drainage every time. The same goes for above-grade walls. If I were offered the choice to upgrade my water control membrane to a fluid, or stick with some inexpensive mechanically attached membrane, but I could pair it with a drainage mat, I'd pick the drainage mat every time. Now, this presumes, of course, that water control is my only concern. What I'd really want is the fluid membrane for better air control and easier detailing, and the drainage mat for the water control benefits. I am, after all, an and person, not an or person, but you get the point. And at the risk of belaboring that point, the same logic stands for roofs as well. Given the choice between a less good product applied over a sloped deck or a superior membrane applied over a flat deck, I'd pick the slope, drainage, every time. And incidentally, it's precisely this principle that makes our typical residential pitched roofs work. There are thousands of penetrations through them. How do you think we attach the shingles? The slope is what makes them work. All of this is to say that the design really does matter more than the material. Now, two last things before concluding. In talking about hydrostatic pressure, I explained that the magnitude of the force is entirely dependent on height, not volume. So an inch of pressure on the Hoover Dam, 1 inch below the surface of Lake Mead, is indeed the same as 1 inch of water on a glass bottle. This is true, but it's not the only factor that matters in building design. Pressure is a function of height, but damage is a function of volume. This is almost too obvious to mention, but sometimes we can become too single-minded about these things. Obviously, we care about the amount of water that our buildings and enclosures are exposed to. Now, similarly, in explaining the importance of dealing with hydrostatic pressure in building design, I'm not attempting to diminish the importance of sealing pathways. The concept of hydrostatic pressure brings important context to our efforts and helps us make better performance decisions overall.